So, to begin with this lecture, the things we wanted to do was to wind up the previous discussion of discrete groups, and from now on we will start with continuous groups. So, let me first write over here. So, I have some slides for this, which basically discuss Young tableaus for rep sizes of irrep sizes, of course, Sn, the symmetric groups. So, there is some method to get the sizes of representations of the permutation groups, and we will just go over this as a tail piece of the discrete group discussion. We did go through, well, I think we will cover it there. I have prepared some slides to do this. The orthogonality main consequence, which is that sigma pi square or Li squared equal to 1, that is the number of classes. So, we saw that the number of classes is equal to number of irreps, and sum of squares of, so there are as many classes as there are irreps, and sum square of the numbers sizes of these is equal to the size of the whole group. So, this title is carried over from the previous, all the conjugacy classes of Sn, but it is just recapitulating some of that. We had done regular cycles, and order n group can be embedded through regular cycles, and representing cycle structures through Young boxes, that is what we will do today. And we had theorem on partitions of the number n, and the number of conjugacy classes is n. So, we had seen that the number of conjugacy classes in Sn is equal to the number of possible partitions of the number n, because it amounts to just saying how many cycle structures you can create. So, each cycle structure is one conjugacy class, right, and therefore, counting the number of cycle structures gives you one conjugacy class. So, we had proved that the cycle structure does not change under conjugacy operation, and therefore, each cycle structure represents one conjugacy class. And so, if we can count the number of such conjugacy classes, that can be done simply by seeing how many ways you can partition n, because that is the way to create cycles. So, number of conjugacy classes is equal to number of partitions of n for the group Sn, and the number of elements in a particular conjugacy class is, we had designated it pi while we discussed the theorems about orthogonality. We said sum over pi times character of that class squared, etc. So, that pi can be calculated as follows. Suppose I have a particular class which contains cycles of length 1, 2, 3, maximum it can have a cycle of length n, and suppose there are lambda r cycles of size r. So, 2 cycles, or 5 2 cycles, or 3 2 cycles, whatever. So, lambda r is the number of cycles of size r, then the size of that particular, the number of elements in that particular conjugacy class is given by n factorial divided by the number of cycles of size 1. If it is lambda 1, then it is lambda 1 factorial times 1 to the lambda 1, 2 to the lambda 2 times 2 factorial, etc. So, this formula we had not actually derived, but it can be seen. It is not very difficult to check this formula from just the definition. So, now I go on to this second part, that representing cycle structures through Young boxes, and we will see that since the one conjugacy class basically stands for one irrep. There is a correspondence between number of irreducible representations and number of conjugacy classes. So, first we represent the conjugacy class using Young tableau, and then we say how to calculate the dimension of the irreducible representation associated with that particular class. So, I am sorry for this word regular occurring too often, but this is what the books write. So, to remain in consonance with them, I have written this. The two books I have referred are Hammermesh, which really has everything, although it is written in a very I mean, it's because it has so much material, I think he didn't have time to be too systematic about the presentation. So, things are really running into each other. So, Hammermesh book and Dresselhaus book. So, Dresselhaus book does not talk about Young tableaus at all, but she has another way of calculating permutations, but the sizes of irreps, but we will do this. Okay. So, the regular rules for filling are that, so let us first look at the example. Suppose I have to deal with S. So, this figure is, can you see the figure? Yeah. So, suppose we are dealing with permutation group S4. Okay. This has it is permutations of 4 different objects. Then what you do is you start drawing 4 boxes and then draw them in various order and then fill them in with numbers 1 to 4. Okay. The rules for filling are as follows. So, I am going back the one transparency. The regular rules for filling are: list all the partitions of n by non-decreasing number of boxes as we go down the rows. Okay. So, take the total number n of boxes and start stacking them sideways and then also downwards, but such that the upper row has at least as many boxes as the next row. So, this is a non-decreasing number of boxes as you go down. I mean in each row. So, this is a row with 2 boxes. So, there can only be 1 and 1 below, or this is row with 2 boxes, below can only be 2. When you get, so you begin with 4 in the row. Then suppose you reduce it to 3, then put the 1 here leftmost. Then suppose you took 2 in the first row, next you can put 2. Then you took 2, there is another way when you have taken 2 boxes in the first row is to stack 1 and 1 in the next 2 rows. But suppose finally you take only 1 box in the top row, then you can only put 1, 1, 1, 1 below. Okay, so this is the way to put the boxes. Then fill these up by numbers 1 to n in strictly increasing order in each row. Okay, top to left to right and also top to bottom. So, here first let us just check that this is according to the system we saw, right. The number of boxes in subsequent rows is strictly non-increasing. Okay, it can be same but not increase. So, then we get these 5 patterns for S4. Now, we start filling with numbers 1 to 4. In the first row, there is only one way to do it in a strictly increasing order 1, 2, 3 and 4. Then in this pattern which is called 3, 1, we can fill 1, 2, 3 and 4, or we can fill 1, 3 and 4 because it is increasing, but we can put 1 and 2. Similarly, we can put 1, 2 and 4 and fill 1 and 3. So, in vertical as well as horizontal directions, the filling is strictly increasing. Then let us look at this. It is 1, 2, 1, 3, 2, 4, or 1, 3, 1, 2, but this also has to be 3, 4. So, you could not have put 1, 4 and 3, 2, because 1, 4 would be increasing downward, but 3, 2 would not be. So, you can only fill in strictly increasing order and use each number only once. So, then this gives this pattern. There are two ways of doing this. Then we go to this format. We can put 1, 2, then we can put 3 and 4 below, there is no other option. If we put 1, 3, then we can put 2 and 4, and if we put 1, 4, then we can only fill 2 and 3. Similarly, when we come to the final format, we can only go 1, 2, 3, 4, there is nothing else you can do. Now, the point is, after filling out, count the number of ways you could fill out. So, in the case 1, for this pattern, there was only one way of filling, so we write that n equal to 1, there is only one way of filling it. Then we write there are 3 different ways of filling this pattern 3, 1, and so we call it n equal to 3, and this one is 2 and so on. Okay, so this gives 2, this has 3 ways, this is 1 way. So, this gives the dimensionality of each of the irreps. There are 5 irreducible representations. Remember that partitions of 4 are 5, so that there are that many conjugacy classes, but therefore there are that many irreps. And now this list is giving the sizes of the irreps. So there is a more formal way, it is called Frobenius Formula, which actually gives some algebraic answer, but this Young tableau method is a simpler way of realizing the Frobenius formula in a pictorial way. So here we find that there are 5 irreps and their sizes are 1, 1, 3, 3 and 2. One particular thing to note about permutation groups, this is specific to permutation groups, is that you will have these conjugate patterns. You will have 3, 1, then you will have a 2 and 1 squared. But if you see pictorially, so it is written 2, 1 squared because 2 in first row, then 1 and 1, so it is 2, 1 squared. This does correspond to 2 cycle, 1 cycle, 1 cycle. This corresponds to 3 cycle and a 1 cycle. But the 3 cycle, 1 cycle and 2 cycle and 2 1 cycles are actually geometrically, visually flipped, rotated versions of each other. Okay. This, if you rotate it by 90 degrees, well, whatever, this if you rotate, let us say clockwise and then flip mirror image, then you will get this. So this pattern and this pattern are conjugate to each other. The first pattern and the last pattern are also conjugate to each other. I can just rotate it clockwise by 90 degrees, I get this. Such conjugate patterns have same sizes, okay, and the 2 squared pattern goes into itself. So it has no, it is self conjugate. The other thing we can now check is that 1 square plus 3 square plus 2 square plus 3 square plus 1 square, that should add up to S4 size, right. So 9 and 9, 18 and 4, 24, 25, 23 and 24, 22, 23 and 24. So we have for the S4 group all of the irreducible representations and their sizes listed by this Young tableau group method. So I have just written compatible with GOT, basically this what I just listed. Some of the, actually I should have written Pi squared, the number of elements in each conjugacy, no, this is the dimensionalities of each of the irreps squared is equal to the order of the group which is n factorial for permutation group. And this, what I already said, the conjugate partitions have the same dimensions, where conjugacy is in this pictorial sense of 3, 1 and 1, and that same pattern rotated becomes this. No, but they are not in same conjugacy class. Structure is different. They are independent conjugacy class. So again, I have put conjugate on in inverted commas. Hammermesh book calls them conjugate box patterns, but it is dangerous because we are using conjugate in too many places. But it is only this geometric conjugacy. It not that it means anything, it's just an observation that if you do apply these. So firstly, we are not going to give the proof of why this process works. We are just giving this as a recipe. I should have written here, I'll just update this file before uploading it. So this is called the Frobenius Theorem, where Frobenius explicitly gives proof of how to count the sizes of the irreps of Sn, of the permutation groups. But when you begin to use this Young tableau, you can see the relation of this box arrangement to this box arrangement, and then you will find that their sizes are same. That is all. There is nothing else that at this point can be said. Probably if we followed the whole Frobenius proof, then we would see why the sizes of these come out the same. Sizes of irreps come out the same. So this is a table taken out of that Mildred Dresselhaus book, table 10.1, the number of classes and listing of the dimensionalities for the irreducible representations of various permutation groups from P1 up to P8. And so we just did this P4, which had 5 conjugacy classes, and one checks that 4 factorial is equal to 1 squared plus 1 squared plus 2 squared plus 3 squared plus 3 squared. Similarly, if we did P5, there would be 7 conjugacy classes, and you will see because of that geometric conjugacy between the box layouts, these numbers are repeated. There are 2 1s, there are 2 5s, well here there are 4 5s, there are 2 9s, there are 2 10s and 1 16. So one gets this total number 720 for P6 and so on. Of course, we are not going to, these are not realistic, we don't really need them, but I thought it's good that at a glance this table has been given. The next thing, so this is basically for this method you should know. I didn't want to include too much enumeration in the up to mid sem, but now we will include it in the tutorial sheet and you should know this. The only comment as I was going through this Dresselhaus book was that we also have, and this is an interesting group. So there is an icosahedral group called designated IH. Icosa refers to 12, I think, 20 headed group, a 20 sided regular polyhedron, and this is the regular truncated icosahedron. So let me show the structure. It is the structure of carbon 60, and so that's why it is important. And actually this author of this book, Dresselhaus, is famous for her work with carbon nanotubes and C60. So this is the cleanest picture to see here. You have a hexagon here and another hexagon and another hexagon, but it has a pentagon as its neighbor on this side. So of the 6 sides, 3 sides, this one and this one, can you see this? Yeah. These 3 have pentagons as neighbors, and the other alternating ones have hexagons as neighbors. This used to be the football pattern. I don't know, they keep changing the football patterns, but some football patterns have this pattern on them, pentagons and hexagons, and they are stitched together in this particular way. And if we see the environment of a pentagon, let us say here, you can see this pentagon. Yeah. So this pentagon has a hexagon, 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 and hexagon. So the pentagon has all hexagons on all 5 sides, whereas the hexagons have alternating pentagons and alternating hexagons. This itself is of course not a regular polyhedron, but it can be got by chopping off the vertices of the irregular icosahedron. So, and this is the structure that, and if you count the total number of vertices, there are 60 vertices on this regular figure. Well, not regular, but this symmetric figure. And amazingly enough, carbon actually forms a structure like this. The one comment made in this book is that ideally, geometrically, these sides are all the same. Okay, the hexagon sides have a particular length and the pentagon lengths are exactly the same. But it need not be, because it's actually from a regular polyhedron you have chopped off vertices. So if you didn't chop them off exactly at the correct point, you can get slightly different sizes. And the author says that the sizes of the hexagon bond lengths are slightly smaller than the pentagon bond lengths. So it's not truly highly symmetric structure in C60, but approximately is. It is 1.2 versus 1.4 angstrom, something like this. So there is a difference, but approximately people are going to treat it as this, and you can deduce a lot from that. You can incorporate the small inequality as a departure from symmetry. First you derive the symmetric thing and then you can treat the next thing as a perturbation. So now this figure also shows the various symmetry axes. If you stand on top of a pentagon, like at this top figure, then you have a C5 axis that you can draw pointing down from you, right? So there are C5 rotation points, then there are C6 rotation points that are here, sorry, C3, I am sorry, we already discussed that, because this hexagon has to be rotated into this hexagon. So if you are on a pentagonal face, then you have C5, you have 5-fold rotation axis. If you are in a hexagonal face, then you have only a 3-fold rotation axis, because there is an alternate of hexagon pentagon pattern. So this is C3, as you can see. Finally, there is a C2 axis shown. This requires a little carefully looking at the whole figure. This is passing through the center of this bond. Okay. So if you look at a hexagon, hexagon, pentagon, pentagon pattern, then this particular bond, which is between the vertices of 2 pentagons, but is a shared side of 2 hexagons. If you stand on top of this bond and through its center send an axis, then you can see that the pattern can be rotated C2, 180 degrees. There is a symmetry of pentagon here, hexagon here, hexagon here. So there is a C2 axis. And there is some other C3 axis shown here, which looks a little more complicated. So one can probably pick up the actual buckyball, as it is called, and see all the details. But its character table is given here. So now that we are experts at reading character tables, we are not scared with all these labels. We are not scared because we are not supposed to remember them. But well, because so these are some notations which I am not emphasizing in this course. Here we are more focused on the mathematics of the group theory, and the applications, if you go to the relevant chemistry or molecular physics or atomic physics course, you will, or solid state physics, I am sorry, not atomic, then you will learn the corresponding professional ways of denoting. But this basically is listing the conjugacy classes and this is listing the various irreducible representations. So, sorry, these are the conjugacy classes. The symmetry operations about the, so there are notes, well you can read them, that is okay. So, she is explaining there is a element I which is an inversion center. So, there are 12 C5s and 12 C5 square operations. So, these are the independent conjugacy classes. Then there are 20 C3s, the 20 hexagons in it, and 15 C2s, those special things passing through bonds and so on. So, these are all the conjugacy classes and all the irreps. The corresponding statement is that this group has 120 elements, but it is not. So, icosahedral group IH is isomorphic to one of these permutation groups, but they are not the same. Okay. So, that is the important thing, and so you have to enumerate the IH separately. It just accidentally has the same number of size as one of the permutation groups. Okay, so this much for this discrete groups. We will end with this nice buckyball example and practical things with it maybe in the exercises. But the main thing, new method that we are emphasizing in this class is this way of calculating the sizes of irreps of the permutation groups. This is not applicable to any generic group, but to permutation groups. We can use Young tableau method to calculate the sizes. Okay, we go to the second half of the course, which is to do with continuous groups. The simplest example of continuous group is the rotation group. Here we do not care too much about the symmetry of the rigid body, so long as it remains the same body. Okay. So, we could have arbitrary shape, but it should not be stretching and deforming, but under rotation it remains the same thing. So, from the point of view of mechanics or dynamics, so all we need is that the rigid body remains the same. No particular symmetry to the symmetry of the shape. And so we can of course rotate. We have an interesting theorem of Euler. That every motion of a rigid body is a translation and a rotation about some axis passing through the rigid body. So, it is rotation, it is translation of the center of mass by some vector capital R, and so you take any rigid body, and this is for any finite motion. You start at some point, you wait for 10 minutes and see wherever it is. You can have space station going around the earth, whatever it is. Effectively, the initial configuration and final one are going to be separated by one displacement vector for its center of mass and a single rotation about one given axis. So, this is important. However, it is tumbling and rotating, the final answer is between the initial shape and the final shape, there is a unique n cap axis about which a single rotation, simple rotation by an angle theta will convert the initial configuration into the final one. So, this is that is why the theorem is interesting, and we can count the number of degrees of freedom in it, because the translation vector capital R has 3 components, and the n cap x, which the unit vector which designates the axis, has 2 independent components, and there is an angle theta. So, totally there are 6 degrees of freedom as we expect. So, this set of operations, the rotations, form a group. Call this the group of dynamics of rigid body, but that is a more elaborate thing, because we know under change of frames, Galilean transformations also the motions have some symmetry. So, for the time being we just note that the rotations by themselves form a group parameterized by three continuous parameters two independent numbers in n cap and one independent theta. We can also see that these 3 parameters are bounded. The values of n cap cannot be infinite because it is bounded to be 1. So, note that nx, ny, nz with sigma ni squared equal to 1 are all bounded zero less than or equal to ni less than or equal to 1, and for theta, and 0 less than or equal to theta less than 2 pi. The rotation is maximum by an angle 2 pi. So, all of these parameters are bounded. This is going to be one characterizing feature of the group, whether the parameters are bounded or unbounded. Okay. That is the nature of this particular group.